Hey guys, here's a quick video on 5.3 notes reviewing properties and laws of exponents. Our set here includes multiplying things with the same base, in which you would add the exponents. For example, 2 cubed times 2 to the 4th is equal to 2 to the 7th. And the reason that that works is 2 cubed is 2 times 2 times 2. 2 to the 4th is 2 times 2 times 2 times 2. So all together we've got 2 to the 7th. When you raise a power to another power, you multiply the exponents. So that would be 2 to the 3 to the 4, for example, is 2 to the 12th. Right? Because you would have 2 times 2 times 2, which is 2 cubed, and you need that multiplied 4 more times. 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2. There they all are, and all together 2 to the 12th. When you have a product, so A times B raised to a power, I'll say it, not that that's actually what's happening, but you can, in a sense, distribute the power to both terms of the product. So 3x to the 7th is 3 to the 7th times x to the 7th. Too often I see this rewritten as 3x to the 7th, which is incorrect, because this is a product, so the 3 is also being raised to the 7th power. 1 to any power is 1. When you raise something to the negative power, you end up with the reciprocal, 1 over a to the s. So we can sneak an example. 2 to the negative 5th is equal to 1 over 2 to the 5th. And kind of that same rule about multiplying things with the same exponent and distributing it, you can undo that, or in the case of the fraction, kind of take it out as well. That's why this other statement is here. This is really, right, 1 to the 5th over 2 to the 5th, so that could be written as 1/2 to the 5th. It's the same. And then anything to the 0 power is equal to 1. So we're just going to play around with a few examples of these and graph a couple of exponentials. So we'll just start with a couple straightforward ones here. Y equals 2 to the x, or f of x equals 2 to the x. Now I'll just make a quick table here for that guy. I could plug in, my favorite is 0, 1, 2, 3, things like that. If I plug in 0 for x, we said anything to the 0 power is 1. And then 2 to the 1st, 2 to the 2nd, 2 to the 3rd, looks like that. I'll sneak in some -1, which we now know is going to be equal to 1/2, because it's going to be 1 over 2 to the 1st power. -2 is going to sneak that in, that's a quarter. So if we plug these guys in, let's see, that's a quarter, that's a half, that's 1, that's 2, that's 4, and that's 8. We have this exponential relationship. And this is going to get infinitely close. Try and straighten that out, but never touch the x-axis. So what exists there is an asymptote at y equals 0. The second one, 1/2 to the x. Again, 0, 1, 2. But by the time I get to 1, which is 1/2, and 2, which is a quarter, I've got about as far as I've gone for the previous problem. So in this case, maybe negative x values which are gonna give me the reciprocal, which is 2, because these are reciprocal functions, the 2 and the 1/2 there. This is going to get me 2, 4, and if I did negative 3, 8. So let's see, 1, 2, 3, 1, 2, there we go. Almost. There we go. 1/2, 1/4. And infinitely close without ever touching. And coming up this way. Looks like that. Also an asymptote at y = 0. This guy, because it's ascending from left to right, if you had to give it a name other than exponential, it's exponential growth. And the ones that go down from left to right are exponential decay. Now, we could be cheeky and throw a negative out in front. And what that's going to do is it's going to flip the graph over the y-axis. And forgive my picture. It's going to look something like that. This red graph, though, is not exponential decay. Exponential decay is this left to right, this kind of soft landing, kind of like that. This one, where it's from left to right, going really, really quickly down, that's an inverted growth. Inverted growth. So don't confuse that with decay, nor should you confuse this graph, which does increase from left to right, but it is not exponential growth. It's as it's moving from left to right, it's flattening out. So that's going to be our inverted decay. Just don't call it growth. Let's see, if we add some other factors here, so we have a graph of f of x equals 2 to the negative x minus 3. And just, let me go back here. The reason that if I've got an equation y equals, we'll say a to the x, I don't know, a to the x. If a, well, let me do this first. If a is greater than 1, like 2 or whatever it was, that's when it's going to be a growth equation. If a is between 0 and 1, like 1/8, a third, whatever, that's when you're going to have a decay. So just to be clear about when that happens. Now, that also assumes a positive exponent, because even though a here is greater than 1, because the negative exponent, this can be rewritten as 1/2 to the x minus 3. So this is actually going to be a decay function. It's going to look like the previous one, except we're going to move everything down 3 units. So where the asymptote was at 0, it's now at y equals negative 3. I can make a table if I want to be confident about plugging in these points. They're all going to be the same points as this guy here, but all the y values are going to be shifted down 3 units. So instead of 0, 1, it's going to be 0, let's see, 0, negative 2. Because anything to the 0 power is going to be 1. 1 minus 3 is negative 2. And because it's a fraction, I'm actually better off plugging in negative values. So that's going to get me, if I plug a negative 1 in here, 1/2 to the negative first is 2. 2 minus 3. There we go, 2 minus 3. Negative 2 in here, 1/2 to the negative second is 4. 4 minus 3. See if I can get this one right. 1. So negative 2, 1. Negative 1, negative 1. 0, negative 2. And we know this thing's coming in for a soft landing there, and otherwise taken off up that way. So decay function that's been shifted down 3 units, which maybe you expected for y equals a to the x minus h plus k. The h and k values behave exactly like they have all year, where if I added some kind of horizontal shift, it would be hooked up with the x in the exponent, and a vertical shift is a k value outside of that. So you'll be asked to graph a few equations, and anything that's otherwise tricky, use the table function on your calculator. Lastly, we'll solve equations with exponents, and we'll start out with ones that are going to be able to be expressed as other base exponents, and then we'll talk about if I can't equate the bases, what do I do? We'll talk about that in the next section, 5.4. But we'll call it number 1 here. Number 1, we have 4 to the 2x minus 1 equals 8 to the x. Now 4 and 8 are related as far as their powers are concerned. 4 is 2 squared, and that's being raised to the 2x minus 1. And 8 is 2 cubed, and that's being raised to the x power. Based using my properties of exponents, this can be rewritten as 2 to the 4x minus 2. Remember, when I'm raising a power to a power, I multiply the powers. So that's where I get 4x minus 2. And then this becomes 2 to the 3x. Now that I've equated the bases, 2 to some power equals 2 to the same power, right? Those two circled expressions need to be equal for the equation to work, so we can equate the powers. Let's see, if I subtract, I get x equals, move the 2 over, x equals 2. We can double check that and plug it back in. I get 4 to the 3rd power, which is 64, and then 8 squared, which is also 64, so that seems to work. Question number 2 involves e as the base. E to the negative x squared equals e to the x squared times 1 over e cubed. And you have a couple options with this second one here, what you want to move around, kind of a lot of choices. I'm going to work e to the negative x squared equals, I'm going to work on that right side and call this e to the 2x, and then that's times e to the negative 3rd. Whether you do that or not is irrelevant. But now that I've got on the right side e being the same base, I'm going to multiply the e's together so I can add those exponents. I'm going to add 2x and negative 3. So this is e to the 2x minus 3. And this is e to the negative x squared. Now that I've got e over here to that power and e to that power, negative x squared must be equal to 2x minus 3. So 0 equals x squared plus 2x minus 3. It's looking like a factor time. Let's see, 1 and 3, x, and I got to get plus, there we go, equals 0. So x equals 1 and negative 3. And then probably worth our while to make sure that both of those work in the equation. They ought to. I don't think there's any restriction that we should be worried about, but e to the negative 1 power, if I plug the 1 in, is e, or 1 over e, excuse me. I get e to the negative 1. And if I plug 1 in here, I get e squared over e cubed, so I would subtract those exponents. That's e to the negative 1. Okay, that works. And then e to the negative 3rd, if I plug a negative 3 in, I get negative 3 squared, which is e to, I get a negative 9 there on the left. And then if I plug a negative 3 in there, what is that? That's e to the negative 3rd squared, so negative 6, which is 1 over e to the 6th, and yeah, e to the negative 9 seems to work out as well. So there's a couple examples where you can equate the bases, and then once the bases are the same on both sides, set the powers equal to each other. It was an important move, even though I have E, E, and E here. It was important that I combined these so that it was clear what powers needed to be equal in this next step. And so that's about it. You're going to now take a look at some of those homework problems, and we will talk more about this on day 2. Enjoy.